Hey, pre-cal kids, this is Mr. Beck. Today we're going to be talking about one of my favorite lessons in trigonometry, which is trigonometry identities. Now, with trigonometry identities, one of the things we want to look at is if we have an expression that is a little bit more complex than it really needs to be, then why don't we find a way of simplifying it before we do a lot of the like plugging in values to see what's going on. For instance, I have two expressions here. What happens if I have the cosine of pi over 4 times the tangent of pi over 4? I can do those manually, but suppose I want to do that with more and more angles. Cosine of pi over 3 times tangent of pi over 3. Let's go ahead and throw in one more. Cosine of 2 pi over 3 times tangent of 2 pi over 3. That would be negative 1/2 times negative square root of 3, which is also square root of 3 over 2. Now, one of the things that hopefully you recognize is these are all ratios that we know. So that means that there is probably a simpler way that we can write this expression. And if you haven't noticed, I've been looking at question 1A. In order for us to be able to say, how can we simplify this just to make our work a little bit less, especially if we have multiple angles to plug in, if we know that tangent is equivalent to sine of theta over cosine of theta, which hopefully you know at this point. We multiply cosine of theta times sine of theta over cosine of theta. The cosines reduce because at cosine over cosine ends up being 1, so they reduce. We're just left with the expression sine of theta. And we could double check that each of the different angles that we applied up here, the sine of pi over 4 is square root of 2 over 2. The sine of pi over 3 is the square root of 3 over 2. And the sine of 2 pi over 3 is also the square root of 3 over 2. So rather than plug in these angles multiple times, all we have to do is plug it in once. So again, the idea behind what we're trying to do today is we're trying to simplify expressions from one form to another. And for me, it's kind of like a little bit of a puzzle as we go through this. And I enjoy math puzzles, I enjoy logic puzzles. So now, before we get to do any of these works, we have to remember some identity, or some of the identities. First identity that I want you to remember is what we call the quotient identities, and it's one that I just used, that tangent of theta is sine of theta over cosine of theta, and then cotangent is cosine over sine. And for those of you who are wondering, well, why is that true? Since, oops, wrong tool. Since sine of theta is y over r, cosine of theta is x over r, then the y over r divided by x over r, multiplied by r, then we get y over x, and that's really just tangent. And technical difficulties really just hit me right there. Not sure why, but my mirroring software just crashed. But we're back. So what I was saying is our goal is to simplify these expressions. Where we're simplifying these expressions has to do with the fact that really these are identities. They are true regardless of what angle we apply in here. Reciprocal identities, these are ones that we've been working with. In fact, we defined cosecant, secant, and cotangent as the reciprocals of the individual functions. So those should be really, really well known. Now, the other three, that if we look at sine as a reciprocal of cosecant, hopefully that makes sense as well, just because they are reciprocals of each other. Pythagorean identities are going to be the most important ones that we're going to have to remember. And I say that because they're used in many, many different ways. I don't know if you remember when we have a circle, x squared plus y squared equals r squared. If we divide everything by r squared, we will get x squared over r squared plus y squared over r squared equals 1. So that would be x over r squared plus y over r squared equals 1. That's where we get sine squared plus cosine squared equals 1. So these Pythagorean identities really just come from the equation of a circle. And what I did was I just proved to you why this was actually true. And that's really our goal. It's to present the information in a way that you're proving that you can take one part of the equation, or at least one part of the expression, simplify it to another part of the expression based off of known identities. So if you remember, we divide both numerator and or all of these by sine squared. We will get sine squared over sine squared, which is 1. Cosine squared over sine squared. Oops, wrong one. Cotangent squared. 1 over sine squared is cosecant squared. Or if we divided all that whole expression by cosine squared, that's where we're going to get cosine squared over cosine squared is 1. Sine squared over cosine squared, which is tangent squared. 1 over cosine squared, which is secant squared. So it comes down to these Pythagorean identities really are based off of the equation of a circle. And so since they're based off of the equation of the circle, they are true. And it's one of these that I hate saying, you're using, or that's true, but it's true. It's been proven true, and because it's been proven true, we can use this fact to our advantage. Now, every once in a while, we will use the even and odd identities. These aren't going to be quite as essential in terms of what we're going to be doing with a lot of our problems, but they can be helpful based off of select problems. So, without further ado, if we take secant divided by cosecant, one of the following approaches is, okay, this does simplify to something else. How would I know what it simplifies to? If we turn everything to sine and cosine, so sine of theta and cosine of theta, by writing it that way, a lot of times it helps. So if we have 1 over cosine of theta divided by 1 over sine of theta, maybe some algebra kicks in. So let's throw some different skills that we're using here. Some algebra says that if we have an expression and we divide by a fraction, so we have 1 over cosine of theta, we can multiply by the reciprocal, sine of theta over cosine of theta, oops, sine of theta over 1, my apologies. Then we put those together, we get sine of theta over cosine of theta, which means this is equivalent to tangent of theta. So secant divided by cosecant is tangent. That's one that's not necessarily so obvious, but at the same time, the more and more you work with it, the more you'll see and understand why that actually works. Something that's going to come up is difference of squares. So difference of squares, I'm not sure if you remember, difference of squares is actually conjugates. So x plus 7 times x minus 7, those are conjugates of each other. That multiplies to be x squared minus 49. Well, what I could do with an expression like what I have in part C is I can factor the 1 minus sine squared into 1 plus sine of u times 1 minus sine of u over 1 plus sine of u. Now, what you hopefully will see is the factor 1 plus sine will reduce with 1 plus sine. We're just left with the expression 1 minus sine. So one of the ways that we're going to approach these kind of problems is to look at conjugates to be able to say, if I have the difference of squares but in trigonometric form, then I can still apply algebra skills to the trigonometry. And then if I have an expression like this, it doesn't seem like there's a whole lot that we could do unless we go down to our Pythagorean identities and say, all right, what is sine squared equivalent to? Well, sine squared of theta is equivalent to 1 minus cosine squared of theta if we take that first Pythagorean identity and just subtract cosine squared from both sides. So let's do that. 1 minus cosine squared theta over 1 minus cosine theta. And then we can factor this just like we did on that problem right there as 1 plus cosine of theta times 1 minus cosine of theta over 1 minus cosine of theta minus 1. And once again, these factors reduce and we have 1 plus cosine of theta minus 1, which is just cosine of theta. So rather than work through this problem and plug in thetas to both of those angles and then do some arithmetic, all we have to do is say, hey, that's equivalent to cosine of theta. And everybody, that's what we're going to be doing. We are going to take expressions that look like this. We will have sine squared over 1 minus cosine minus 1 equals cosine, and it's our job to prove that the left side equals the right side or the right side equals the left side. You're going to be able to choose which one. But it's going to be your job to prove that what we have on one side equals what we have on the other side. And that's what I have here in my notes, where if I have two functions which are identically equal, basically I'm telling you these two functions are identically equal to each other. If we have these two functions are equal to each other, how do we prove that one side equals the other side? When we prove one side equals the other side, and maybe an expression like this, if we multiply this out 4 times, we can prove that that equals this side. Or if we factor g of x 4 times, we can prove that that equals the x minus 2 squared. So one of the benefits that we have is we really can work on either side. So we can work on either side, but the important thing is we can only work on one side at a time. You do not want to work on both sides at the same time because it is not an equation. So we're not solving them like equations. They're not equations, even though they look like equations, but these are identities. So let's do this. If I have tangent times cotangent minus sine squared equals cosine squared, one of the approaches I take to these problems is I say, which side is the more difficult side? Because the more difficult side is the one that we could reduce to the simpler side. It's a lot harder to take an easy thing and make it more complicated. It's a lot easier to take complicated things and break them down slowly into something easier. In fact, that's a great life skill for you. So tangent of theta times cotangent of theta minus sine squared. What I like to do is I like to draw a line down to represent that you cannot pass. So really Gandalf should be the one who does, or who's like at the top of my nose, but you shall not pass. If we work on the left side, tangent times cotangent. I'm not sure if you know what tangent times cotangent equals. Let's pretend that we don't. Tangent is sine of theta over cosine of theta. And if we multiply that by cosine of theta over sine of theta, then what's going to happen is we could see that both of these reduce, and tangent times cotangent really is equivalent to 1. So now I have 1 minus sine squared of theta, that my goal is to get it equal to cosine squared of theta. Well, how do I do that? This is where I can use the Pythagorean identity. So the Pythagorean identity, 1 minus sine squared does equal cosine squared. So let me write that down, just in case you don't know that one. So 1 minus sine squared is cosine squared. So if this does equal cosine squared theta, then now I have cosine squared equals cosine squared. I like to put a check mark to show that that's what I was trying to prove. And a lot of times we like to write QED, which is that which was meant to be proven. So it's Latin, shorthand for Latin. All right, next expression, 1 minus cosine squared times 1 plus cotangent squared. Now, if this equals 1, definitely this means I probably want to work on the left side, because if I start just with 1 and say, hey, turn that into the other side, that's probably going to be a little bit difficult. So let's take this in a simpler way. There are a couple different approaches that we could take here. Now we could throw in some algebra and say, yes, we're allowed to FOIL this out. So 1 times 1 times cotangent squared, cosine squared, negative cosine squared times 1, and 1 negative cosine squared times cotangent squared. So we could do that, and that will work. I have no issues with that. And that's one of the beauty of these problems, that you don't necessarily have one approach to these problems. What I prefer to do is to say, okay, 1 minus cosine squared, and it's kind of the hint. If I have a trig and I have a squared, there's probably a Pythagorean identity that I have. And if we go back to our Pythagorean identities, I'm not sure if you can see it yet. If we go to our Pythagorean identities, 1 minus cosine squared is equivalent to sine squared. So this is sine squared of theta. And 1 plus cotangent squared, if I look and I say, okay, do I have 1 plus cotangent squared? Why, yes, I do. That's equivalent to cosecant squared. So this is cosecant squared of theta. And now, if I remember, the cosecant squared is really 1 over sine squared. Now I have sine squared of theta times 1 over sine squared of theta. And that's where I get my 1 equals 1. Check QED. So, well, I could have FOILed these out right from the beginning. That would work, and I'm very happy that this could work. There are alternate approaches. I try to find the most efficient approach possible, just because I think that that's really one of the goals of mathematics, is how do we think through things very efficiently. Now, if you're not seeing it in the same way that I'm doing it right from the beginning, don't worry, because I've had plenty of years of practice. And while you might not have had that practice yet, that doesn't mean that you cannot do it. So my goal is to help you become the mathematician that I see inside of you. But anyway, enough philosophy. Sometimes one of the approaches that we could take, and there are lots of different approaches that tend to be beneficial. One of the biggest approaches is to say, let's multiply by a creative 1. Now, what do I mean by a creative 1? Well, the idea behind the creative 1 is, if I multiply, or if I take a look at this part of the expression, sine squared over 1 times 1 over sine squared, we get sine squared over sine squared, which is equivalent to 1. So there might be a case where I want to multiply an expression by sine squared over sine squared, which is equivalent to 1. Now, keep in mind, this is equivalent to 1, but I'm not changing the expression. I can't just say, hey, let's add 3 to one side, because then I'm changing the expression. Kind of like saying, hey, let's throw $1,000 in my bank account just for fun. Not me, just to like randomly change it by $1,000. I think the bank might have a little bit of an issue with that. So we can't change a problem. We just have to change what it looks like. So the approach we say is, okay, how do we change what it looks like? Let's go back to what I said is, which side looks more complicated, left side or the right side? And I will argue that I'm more familiar with sines than I am with cosecants. So let's go ahead and work on the left side and see what happens. So I know that cosecant, okay, what do I know? That's the reciprocal of what? That is the reciprocal of sine of theta. So if I write this as 1 over sine of theta minus 1 over 1 over sine of theta plus 1, now I could look a little bit deeper and say, okay, is there a creative 1 that I can multiply by in order to simplify this expression? And through the course of the year, we've talked about fractions within fractions. One approach that I like to take is I would like to multiply by the least common denominator of the numerator and denominator, which would be just sine. That is the creative 1 that I'm talking about. So if I multiply by sine over sine and now distribute, notice how there's some algebra built into what we're doing. Sine times 1 over sine is 1. Sine times 1 is sine. Sine times 1 over sine is 1, and sine times sine is 1. And if you notice, that's exactly what I was trying to prove this equals. So check Q, E, D. So 1 minus sine over 1 plus sine. And again, the creative 1 here was sine over sine. How did I know to do that? Sometimes it's helpful to turn all of our trig functions into either sine or cosine so that we can help. Let's take an expression B, secant minus cosine over secant plus cosine, versus sine squared over 1 plus cosine squared. So when I look at sine squared over 1 plus cosine squared, it's really hard for me to figure out what that's going to be equal to. So let's take a look at the left side again. That left side involves some mixture of secants and cosines. That's kind of a clue to change to sines and cosines. So secant is 1 over cosine of theta minus cosine of theta. Secant again is 1 over cosine of theta plus cosine of theta. And our creative 1 in this case is, let's multiply by cosine over cosine. When I do that, once again, I distribute. In my numerator, I get 1 minus cosine squared. In my denominator, I get 1 plus cosine squared. Now I'm kind of close to what it is I'm trying to solve. Notice how, or not solve, but simplify. Notice how these two are equivalent. Since those are equivalent, I don't have to do any work on the denominator. My goal is to make the 1 minus cosine squared equivalent to sine squared. I really don't have to work that far when I know the Pythagorean identity. It's sine squared of theta over 1 plus cosine squared of theta equals sine squared of theta over 1 plus cosine squared of theta. So, proved what I was directed to prove, QED. Now, in a problem like this, the creative 1 is not quite so obvious. And if I take a look and think the other approaches I took the problems, these are already in terms of sines and cosines, so I can't really do anything differently or I can't like use any of the reciprocal identities. So there is a very directed approach that we're going to take with these problems. That directed approach is hinted at me by the fact that this is 1 minus sine and 1 plus sine. That hint is we multiply by the conjugate. If you notice, I mentioned the conjugate earlier in the beginning problems because this is a very, very common approach that we're going to take. Now, it doesn't matter which side we work on, so I'm going to choose to work on the right side this time because I just haven't done that yet. So if I multiply by 1 minus sine over 1 minus sine, then I get the expression cosine times 1 minus sine. Notice how I'm keeping it factored because there's not really a sense in me multiplying that through. So there's no point in multiplying it through, especially when I look at the left side. By the way, that's one of the things that we like to do. Use the other side to help us. It's kind of like you students who as you are working through a problem, you look at the answer in the back of the book and you say, oh, I need to make my answer look like the answer in the back of the book. You guys should be thriving off this lesson like no other. So anyway, I'm going to keep this factor. Now in the denominator, I'm going to multiply that through, and we get 1 minus sine squared. And everybody, that is the big idea. We multiply by the conjugate, so we have the difference of squares. Now this time, I am going to change the 1 minus sine squared into cosine squared because that is the Pythagorean identity. And now, if you notice, I have a cosine over a cosine squared, and if I reduce those, I will get 1 minus sine of theta over cosine of theta, which is what I was trying to prove. Now, this is, as I mentioned right at the beginning of this problem, this is a very directed approach to a problem. but it shows the power of conjugates because when we take a look at our Pythagorean identities will be full of conjugates if we say that tangent squared is secant squared theta minus 1, or the difference of squares. We could also say cotangent squared theta is cosecant squared theta minus 1. So if there's a way that we can get it and use the difference of squares by multiplying by the conjugate, it's going to allow us to use the Pythagorean identities. Moving right along, we can work either on the left side for this problem or the right side. Notice again when I'm hinted at cosecant minus 1 and cosecant plus 1. So let's go ahead and let's work on the right side again. So if we multiply by cosecant theta minus 1 over cosecant theta minus 1, my numerator is cotangent of theta times cosecant theta minus 1. My denominator is cosecant squared theta minus 1. So cosecant squared theta minus 1, let's go back to the Pythagorean identity that I just wrote out. That would be cotangent squared. So if I replace the cosecant squared minus 1 with cotangent squared of theta, now I get a situation just like the problem before. And as I said, this is a very directed approach, but that directed approach happens quite a bit. Cotangent of theta. So that's what I was trying to prove, cosecant theta minus 1 over cotangent theta. So check Q, E, D. And notice, once again, I'm working only on one side of the equation, not on both sides, because this isn't really an equation. This is an identity that we're trying to prove. All right, well, what happens if I have an expression like this? Now, an expression like this, what jumps out at me is this is not quite as simple. And I say simple, not to say, oh, these are the easiest things ever. I'm saying it's not quite as simple of an expression because there's a lot of things going on. So one of the ideas that I tend to look at is I have two different terms here that are being subtracted, and they combine together into one term. If I have two terms combining into one term, what that means is maybe algebraically, let's find a common denominator and join these together. So if I find a common denominator, that common denominator is sine of theta, cosine of theta. So I have to multiply this term by cosine theta over cosine theta. That's your creative 1 again. I have to multiply this term by sine of theta over sine of theta, the creative 1. And what I get is cosine theta times sine of theta plus cosine of theta minus sine of theta times cosine of theta minus sine of theta all over sine of theta cosine theta is going to equal the other side. Now let's go ahead and line this up just a little bit better. That's on me, not you guys. So now that I have that lined up, is there anything I could do? I'm not seeing it quite right away. So let's go ahead and distribute. So now I have sine of theta, cosine of theta. I tend to like to write the sine first. You don't have to. Plus cosine squared theta minus sine of theta, cosine of theta. And then please note that it's going to be minus times a minus, which is plus sine squared of theta over sine of theta, cosine of theta. Now, where do we go from here? I see a positive sine cosine and a negative sine cosine. So now I'm left with cosine squared theta plus sine squared theta over sine of theta, cosine of theta equals. And, well, let's see, where am I at? My goal is to make this equal to secant and cosecant. So if my goal is to make this secant and cosecant, I really need to have 1 over cosine here, and I need to have 1 over sine, which, if I use a Pythagorean identity, I do have that, 1 over sine of theta times cosine of theta, which we don't necessarily have to write this step unless you want to. 1 over cosine times 1 over sine. That's where you get the secant of theta times cosecant of theta. Basically, if you want to go directly from here to here, I'm okay with that. So that equals secant of theta, cosecant of theta. Check Q, E, D. Well, take a look at this expression. And one more time, I see that I have 1 term, 2 terms, which simplify into 1 term. That's my clue of let's find an LCD and join these together into one big happy expression. So the happy expression should have the LCD of cosine of x and 1 plus sine of x. So that's what we do. We're going to multiply 1 plus sine of x times 1 plus sine of x plus cosine of x times cosine of x over the common denominator of cosine of x times 1 plus sine of x. Now, for those of you who wondered, I multiplied by cosine over cosine, the creative 1. I multiplied this by 1 plus sine over 1 plus sine, which again is that creative 1. And so where do I go from here? I don't see any way of avoiding foiling through. So we have 1 plus sine, so that would be plus 2 sine of x, then plus sine squared of x, plus cosine of x, actually that's cosine squared, over cosine of x times 1 plus sine of x. Notice that I'm leaving my denominator factored, and the reason why I'm leaving my denominator factored is because my hope is I can reduce some kind of factor. How do I know that? That's kind of the big important detail. How do I know that? The fact that I have cosine in the denominator is going to model the right side where I have the secant. So that cosine is going to end up staying there. What's not going to stay there is the 1 plus sine. So how are we going to get rid of that? I don't know yet. Let's continue on with the problem. Our Pythagorean identity, sine squared plus cosine squared, means I have 1 plus 2 sine of x plus 1 over cosine of x times 1 plus sine of x. And I hope some of you are seeing what's happening now. This is 2 plus 2 sine of x over cosine of x times 1 plus sine of x. And I can factor out the 2, and I'm left with 1 plus sine of x over cosine of x times 1 plus sine of x. And boom, there's where we get our reducing. And we're just left with 2 over cosine of x, which we could write as 2 secant of x, which is what we were trying to prove. Check, Q, E, D. Now, you might think that I'm making these problems look simple, and I will tell you, they're not necessarily simple. I've worked with a lot of these problems over the years, so my experience has helped me. My hope is your experience, it helps you. There are times that I work through some problems and I get nowhere, and that's okay. It's all about going back and saying, let's try something else, I kind of call this a video game mentality. You're at a boss you've never fought before, you fight them, you die. Well, then you say, okay, let's fight that boss again, see something else. Doesn't work, try something else, and eventually you'll figure out something that works. And then you learn those strategies, and video games use these strategies to help you build your skills so that you can fight even harder things. So these problems are like video games in my mind, that it's training us to try to find other approaches to come up with common solutions. Basically, I'm beating the boss at the end of the game. So let's take our last set of identities. So the identity I have here is tangent of alpha minus cotangent of alpha over tangent of alpha plus cotangent of alpha plus 2 cosine squared equals 1. Which side is the more complicated one? I hope you guys recognize the left side is more complicated. Now, where do I go with this? I don't know. The fact that I have plus cosine squared equals 1 tells me that there's probably going to be a Pythagorean identity there. Well, what is that Pythagorean identity? I don't know yet. Let's work through it. I'm mixing tangents, cotangents, and cosines, so let's change everything to sine and cosine of theta. So tangent is sine of alpha over cosine of alpha minus cosine of alpha over sine of alpha all over sine of alpha, cosine of alpha, and then plus cosine of alpha over sine of alpha plus 2 cosine squared alpha equals. All right, I'm not sure if that helped you. It kind of helps me because once again, this brings us into a fraction over a fraction. And I told you with a fraction over a fraction, I like to multiply by the LCD of all of my inner fractions. So cosine of alpha, sine of alpha is the LCD of all my inner fractions. So if I multiply cosine of alpha times sine of alpha times that term, then I will get sine squared of alpha. If I multiply here, the sine of alphas cancel, and I'm left with minus cosine squared of alpha over, let's go ahead and distribute here. The cosine squareds cancel, and I'm left with sine squared of alpha. Here, the sine of alphas cancel, and I'm left with cosine squared of alpha. So they reduce, I shouldn't say cancel. Bad Mr. Beck. And that's alpha non next. So we know that sine squared plus cosine squared is equivalent to 1. So it's sine squared of alpha minus cosine squared of alpha over 1 plus 2 cosine squared of alpha. And the fact that these are over 1 means we can kind of get rid of that and it's going to be okay. Now I have minus cosine squared plus cosine squared, or plus 2 cosine squared, which turns into sine squared alpha plus cosine squared of alpha. So 1 equals 1, check, Q, E, B. Continuing on, the fact that I have a bunch of terms in here that are like terms in the numerator, terms in the denominator that simplify to just one simpler fraction, let's go ahead and turn this into sine of v over cosine of v over cosine squared v minus cosine of v over sine of v. Notice how I keep doing the approach of if I'm mixing tangents, cotangents, secants, and cosecants, and sines and cosines, let's put everything in terms of sine and cosine to make life easier. So in this situation, I have fractions within fractions. So let's multiply by the LCD. So the LCD is cosine of v times sine of v. Denominator, same thing, cosine of v times sine of v. So what happens if I do that and I distribute, I now have cosine of v sine cubed of v, I'm kind of worried here, minus sine squared of v. I've never seen that before. Please don't freak out. Hopefully you'll see where we're going with this. Cosine cubed v times sine of v minus cosine squared of v. So, okay, I have cosine times sine cubed minus sine squared. Where can I go with this? I have sine squared that's really a factor of both terms in the numerator, so let's take that out. Sine squared of v, and I'm left with cosine v sine of v minus 1. I have a cosine squared that I could factor out of the denominator, and I'm left with cosine v sine of v minus 1. And oh, beautiful, these reduce. I now have sine squared of v over cosine squared of v, which is equivalent to tangent squared of v. So, yay, I got what I wanted. Now, I wasn't fully sure where I was going with that, but I ended up there. So everybody, please don't say that I know exactly how to get from beginning to end right at the start. You're not always going to be able to do that. Sometimes it takes multiple approaches to get to where we want to be, or multiple steps to get to where we want to be. So, next problem. Secant minus tangent squared plus 1 over cosecant times secant minus tangent. Wow, this is a lot. What approach should we take? Definitely let's work on the left side because that's far more complicated. So what I'm going to do is let's go ahead and multiply this out. So we're going to FOIL this out. That FOILs to secant squared w minus 2 secant w tangent w, and then plus tangent squared w plus 1. So I FOILed out the numerator. And should I distribute my denominator or not? I really don't know off the top of my head. So let me just keep it factored and see if that's going to help me. And everybody, I actually do know where we're going with this. But at the same time, if you don't know, you can either distribute it or not. Maybe you distribute, you realize you have to factor. Okay. If you distribute and realize you have to factor, no worries, just go ahead and refactor it back out. It's nice when we can do this in the simplest amount of steps, but take as many steps as you need, please, please, please. So where can I go from here? Okay, I know that tangent squared plus 1, if I use my Pythagorean identity, is equivalent to secant squared. So now I will have, and I'm going to cut to the chase here, my numerator becomes 2 secant squared w, which is what I have there, minus 2 secant w tangent w over my denominator, cosecant w times secant w minus tangent w. All right, so, should I distribute or not? That's not my question. Is it going to help me? Well, this is where we could say, you notice that secant is a factor of both terms in the numerator. In fact, 2 is also a factor, so let's factor out a 2 secant w, and we're left with secant w minus tangent w. Brilliant. You see how those cancel each other out, or reduce out, should not say cancel. Once again, bad Mr. Beck. So now I have 2 secant w over cosecant w, which is supposed to equal 2 tangent w. If you remember, we sort of did a problem like this right at the very beginning, where this is going to be 2 over cosine of w, all over 1 over sine of w, which if we multiply by the reciprocal, which is sine of w over 1, sine of w over 1, this just does give us 2 tangent of w, and that's exactly what we wanted. Yay, check, Q, E, D. Now, I kind of got lucky in terms of how I saw that, but the question is, do you see it? Do you see all those steps? And the more you work with these, the more you're going to be able to see it, but that doesn't mean you're going to see it right away. In fact, that was a little bit more efficient than the last time I took an approach to that problem. So, go Mr. Beck. All right, so let's take a look at the problem that I have here. Now, if we know more trig that we're about to do later on, this problem would be a heck of a lot easier. But we don't know it yet, so it's not quite as easy. Where do we go with this? First, we take a drink of water. And then, everybody, where do we go? One of the things that I notice here is my denominator is full of cosine of the fourth minus sine of the fourth. That is the difference of squares. So I probably am going to be multiplying this numerator out. I don't know yet. I'm just saying, what do I see? I could factor this into cosine squared beta minus sine squared beta times cosine squared beta plus cosine or plus sine squared beta. Now, does that help me? My thought was that did look like a difference of squares. Great. I do know that this is a Pythagorean identity. Cosine squared plus sine squared does equal 2 cosine squared beta. Does equal 1. So my denominator is now just going to be cosine squared beta minus sine squared beta. And I will say I do have a little bit of knowledge here that cosine squared minus sine squared is going to be something common that we're going to be using. But I'm going to do a specific trig substitution that we did when solving equations. If you remember, sine squared of theta equals 1 minus cosine squared of theta. That's the substitution I'm going to do here. And again, it helps when you understand the problems and you've seen enough of these to figure out where to go. You might not get there right away, but that's okay, step by step by step. Cosine squared beta minus 1 minus cosine squared beta. If we have that minus and minus, don't forget that's going to distribute into, actually let me rewrite the numerator first. That's going to distribute into a positive 2 cosine squared, and I put theta there instead of beta. My apologies. So that's going to be 2 cosine squared minus 1. And if you see, I will have 2 of those in the numerator, 2 of those factors in the numerator, 1 in the denominator. So now I have 2 cosine squared beta minus 1. And what am I trying to make it equal to? I'm still trying to make it equal to 1 minus sine squared of beta. So how do I do that? Let's go ahead and do a substitution. How do I turn cosine squareds into sine squareds? I know that cosine squared is 1 minus sine squared. So let's do that. 2 times 1 minus sine squared of beta minus 1. And distribute 2 minus 2 sine squared beta minus 1, which turns into 1 minus 2 sine squared beta, which is what we were trying to prove right from the beginning. So yay, I made it. There were a lot of steps there, but I made it. And we celebrate all of those little victories. So this is Mr. Beck signing off.